Solutions, Level 3. In this video, we're going to continue verifying solutions to ordinary differential equations and determining appropriate intervals of definition. These problems will be slightly more challenging than the previous video. Let's go ahead and jump straight into the first example. Verify that the indicated function is a solution of the given differential equation. Find an appropriate interval I of definition for each solution. The differential equation y prime equals 25 plus y squared. And the function we need to verify is y equals 5 times tangent of 5x. Alright, scanning the ODE, we see that we need to find the first derivative of the function. I hope you remember how to take the derivative of trigonometric functions. If you don't, you can always go back and look at the videos under Calculus 1. Alright, the first derivative of this function requires an application of the chain rule. Applying the chain rule, we obtain the following expression. Next, we go ahead and substitute the function and its derivative into the equation. Doing that, we obtain the following. Next, we need to simplify the left and right-hand side of the equation and check to see if both sides are equal. So we go ahead and square the expression on the right side of the equation. Doing that, we obtain the following. Next, we factor out 25 from both terms on the right side of the equation, as follows. Here we need to use a Pythagorean identity and replace 1 plus tangent of 5x squared with secant of 5x squared. Doing that, we obtain the following expression. Notice that both sides of the equation match. This means that the function is indeed a solution to the ODE. Now let's assign an interval of definition. Let's take a look at the graph of the solution. Recall that tangent can be expressed as the quotient of sine and cosine. In this form, it is clear that we can't have any values of x that makes the denominator equal to 0, since division by 0 is undefined. In other words, the function is not defined when cosine of 5x equals 0. This means that 5x cannot equal pi over 2 plus any multiple of pi. Recall that trigonometric functions are periodic. By solving for x, we see that x cannot equal pi over 10 plus any multiple of pi over 5. At these values of x, we would expect to find vertical asymptotes. Since we want our interval of definition to be as large as possible, we have various intervals to choose from. One region can be the interval from negative pi over 10 exclusive to pi over 10 exclusive. Or the interval can be from pi over 10 exclusive to 3 pi over 10 exclusive, and so on. Notice that the graph of the derivative also contains a similar domain, and thus would have a similar interval of definition. I invite you to explore this on your own. Alright, let's try the next example. The differential equation y double prime plus y equals secant of t, and the function to verify is y equals cosine of t times the natural log of cosine of t plus t times sine of t. Alright, notice that we need the second derivative of this function. So let's first find the first derivative. We will need to apply the product rule along with the chain rule to find the first derivative of this function. In the end, the derivative is equal to the following expression. Next, we go ahead and find the second derivative, which also requires an application of the product rule and chain rule. In the end, the second derivative is equal to the following expression. After that, let's go ahead and substitute the function and its second derivative into the ODE. Doing that, we obtain the following expression. Simplifying the left-hand side of the equation, we obtain the following. Next, we go ahead and add the two terms on the left-hand side of the equation. To carry out the sum, we need to find a common denominator before we add the numerators. Doing that, we obtain the following expression. Now we can replace the numerator with 1. Recall that the Pythagorean identity sine squared plus cosine squared equals 1. Replacing the numerator with 1, we obtain 1 over cosine of t. This term can be rewritten as secant of t, which is equivalent to the right-hand side of the equation. This means that the function is indeed a solution to the ODE. Now let's determine an appropriate interval of definition. Notice that the solution contains a natural logarithm. For the most part, the domain of logarithms is dependent on the argument. In this case, the value inside of the argument has to be greater than 0. In this case, cosine of t has to be greater than 0, meaning we only want values of t that generate positive values of cosine. Recall that this occurs in quadrant 1 and quadrant 4 of the unit circle. Taking a look at the graph of the function, an appropriate interval of definition is the interval from negative 5 pi over 2 exclusive to negative 3 pi over 2 exclusive, or negative pi over 2 exclusive to pi over 2 exclusive, or the interval from 3 pi over 2 exclusive to 5 pi over 2 exclusive, or any other interval that lies between quadrant 4 and quadrant 1. The domain for the first and second derivatives is essentially the same as the solution. We have the freedom to choose any of these intervals as long as they lie between quadrant 4 and 1 of the unit circle. Alright, let's go over the final example. The differential equation y prime minus 2 times ty equals 1, and the function to verify is y equals e raised to the power of t squared times the integral from 0 to t of e raised to the power of negative s squared ds plus e raised to the power of t squared. Alright, you might have seen functions of this form way back in your first calculus course when you were introduced to the fundamental theorem of calculus. We will have to invoke it once more in order to find the derivative of this function. Looking at the ODE, we see that we will need the first derivative. We're going to need to apply the first part of the fundamental theorem of calculus, along with the product rule and chain rule, to find the derivative of this function. Carrying out these operations, we obtain the following expression. The first term of the derivative can be simplified as follows. It's just a matter of applying the exponent rules that you learned way back from Algebra 1. This expression simplifies as e raised to the power of 0, which is equal to 1. Alright, having found the derivative, we go ahead and substitute the function and this derivative into the ODE. Doing that, we obtain the following expression. Next, we go ahead and simplify the left-hand side of the equation. We first distribute negative 2t. Doing that, we obtain the following. Next, we simplify by collecting like terms. Notice that the integral term cancels out with the negative integral term, and the positive exponential term also cancels out with the negative exponential term. Simplifying the expression, we are left with 1 equals 1. The left-hand side equals the right-hand side. Hence, this function is a solution to the ODE. The last thing to do is to find an appropriate interval of definition. For the most part, the domain of exponential functions and power functions, such as x squared, is all real numbers. The graph of this function is represented as follows. This function is essentially defined from negative infinity to positive infinity, and this will be our interval of definition. Alright, in our next video, we're going to go over a couple of examples and verify the solution of partial differential equations.